Okay, so welcome back to this exploration of exponents to find out how they behave in this part of the math world. The skill required to be able to understand the concept in this video is to be able to rewrite expressions in compact form, or also be able to write expressions in expanded form. Here we're starting with expanded form, obviously. You can recognize that. If you don't know what I'm talking about, please refer to first episode of this series, and there's detailed explanation of those terms. All right, so here we go. Let's get started. The first thing to identify is, do you recognize the same base? Yes. And do you recognize multiplication, repeated multiplication? Yes, because this right here also means multiplication. And what's the common base? What is being commonly multiplied by itself? It's a 5. And let's count how many 5s are being multiplied by each other. Ready? Count with me. 1, 2, 3, 4, 5, 6, 7. So what's the exponent for this 5? Is 7. This is 5 to the power of 7. 5 to the 7th is the compact form. This is the expanded form. This is the compact form. All right, let's work on this expanded form. What is the common base of that? Or what is the common factor that is repeatedly being multiplied? It is x. And therefore, we're going to count how many times that is being multiplied by itself. It is 1, 2, 3, 4, 5, 6, 7, 8, 9. So that should be x to the power of 9. I'm writing the exponent in green so you can identify it. That's the key thing to be looking at right now or thinking about. Great. So we know this is the compact form. This is the expanded. These two are equal to each other, just like these two are equal to each other. But I want to show you another approach that's going to make our lives very convenient in the future for our practice. And it comes in the terms of, notice how I purposely wrote something times some other bigger something, something times something. So can we simplify those individually? And the nice thing is that for both of them, what's the common base common for these three? It is 5. So we can write it as 5 to the some power, just like we can write this one as 5 to the some power. And let's figure out in blue, I'm going to write how many times was the 5 multiplied by itself? It was 3 times. Therefore, this is 5 to the third. All right. And in yellow, for the second expression, how many times was the 5 being multiplied by itself? It was 4 times. So therefore, this is 5 to the power of 4. And what's happening between them? They're still being multiplied. So it's 5 to the third times 5 to the fourth. That should equal something. Let's write an equation that we already know it's equal to. On the right side is 5 to the 7th. So we know that 5 to the 4th, and I'm doing it this way on purpose, color coding it so you can see 5 to the 3rd times 5 to the 4th. Let me readjust this. There we go. That looks a little bit better. 5 to the 3rd times 5 to the 4th equals 5 to the 7th. Do you see a relationship between the exponents? Think about it. How can a 3 and a 4 of exponents give you an exponent of 7? Let's see if that also holds true on the next one. So we know that all of this simplified to a x to the 9th expression. But if we think about the same way, can we simplify this left expression first, write it with the same base of x? So this must be x to the some power times x to the some power on the right expression. How many times was x being multiplied by itself in the first expression? It looks like 4. So therefore, this is x to the 4th power. And the second expression, how many times was the factor multiplied by itself? 1, 2, 3, 4, 5. Therefore, this is x to the 5th. And we know it was multiplication, so therefore x to the 4th times x to the 5th must equal what the expression was on the right side. Let's put those pieces of the puzzle together. That looks something like this. All right, and we know that that should equal to x to the 9th. These two are equal. And again, the main thing to focus on is, how did an exponent of 4 and 5 give us an exponent of 9? What's going on there? First of all, you should notice all of the bases are the same. X, X, and X didn't change. 5, 5, and 5, the base didn't change. But how did the 3 and the 4 equal a 7? How did they 4 and the 5 equal a 9. What operation did we do is, because at some point, look, we're not going to expand 12 of them and rewrite 10 of them. That would waste a lot of time. So we want to think of a shortcut, and hopefully you notice that 4 plus 5 is 9, or 3 plus 4 is 7. And how do I remember that? I associate addition with what operation does this indicate? This indicates multiplication, so you should start to associate multiplication with addition, especially when we're multiplying the same base. That's the key question that we're going to keep in mind here, all right? When we're multiplying the same base, we can use that idea. And look, I guess here we could have said the same thing. Now I'll write it just in green. This is 2 over 3 to the second power, and the second something is 2 over 3 to the third power. But if you forgot that, oh, I can add the exponents when I'm multiplying the same base, then at least we can say, all right, with the expanded form, we can make that into compact. How many 2/3? 1, 2, 3, 4, 5. So we know that this is 2 over 3 to the fifth power, which is the same as what's on the left side. And again, look, it's very consistent. 2, the exponent of 2 plus an exponent of 3 should equal an exponent of 5. That's the main idea. It checks. So let's start applying that shortcut, because again, we're not going to rewrite this 13 times or 12 times. The nice thing is we recognize same base. That's the main idea. Multiplication, that's the next thing you should check. And then exponents, we can add them. So this means this can be rewritten as 7 to the 12th plus 10. Notice how that's the whole exponent, 12 plus 10, and that should equal 7 to the 22nd power. We're not going to worry about what is the multiplying this out. Even a calculator might have trouble with that. So they'll give it to you in scientific notation. So that's why we will leave it in this compact form. That's excellent. And we recognize the same thing on the next one, that the base is the same. So we can write this as 2 to the 13 plus 12. And that gives us 2 to the 25th power. And again, that's a really large number, so we'll leave it in that form right there. That's excellent. But that's the main idea. Multiplying the same base, we can add the exponents. Keep that in mind. Multiplying the same base, yes, then we can add the exponents. The key for this one is identify that the exponent implied is 1. So therefore, this is P. The more you do this, the faster you'll do it in your head. P to the 16. There we go. And I'll give you an example of where we're going with this. This is not the emphasis of this lesson. It was what we've already talked about. Same base, multiplication, add their exponents. That's the key, all right? So therefore, this one right here is, what is the same base? It's not 3 and it's not 5. The same base is x. X to the 8th times x to the 6th. We can say that part simplifies to x to the 14th. Remember, same base, multiplication, we can add their exponents. 8 plus 6 is 14. But 3 and 5 are not exponents, they're coefficients. So just think of them like 5 times 3 is 15. And we'll do more examples like this in the future practices. But the main idea is same base, multiplication, add their exponents. And that's the key question, which I've already answered so many times, but that's the key question. When can we add exponents? A few things need to be true. We've already said them. All right. When can we add the exponents? It has to be same base and multiplication involved. All right. There it is. That's one of the key ideas, which leads perfectly into the next one. And I want you to start thinking opposite. If multiplying the same base was associated with addition, start thinking the opposite of that. What's the opposite of multiplication? And start thinking, what's the opposite of adding exponents? We might talk about that soon. So let's see some expanded form so that we can look for a shortcut as well here. All right, so here we have that 4 times 4 times 4 times 4 times 4 over 4 times 4 times 4. All right, that's kind of crazy looking. But the thing is that at least we recognize they're all the same base, and we have division going on here. So here's one way we can first think about this. We can say, all right, we can rewrite this in compact form. The numerator, let's focus on that one first. And yeah, we're gonna say 4 over 4 to the something over 4 to the something. Let's count in blue. how many 4s were multiplied on the numerator? How many times was that multiplied by itself? It was 1, 2, 3, 4, 5. So we're going to have a 4 to the 5th divided by 4 to the 3rd. Okay, but we don't really have a rule for that yet. But the nice thing is that we do know how to divide things like, what's 5 divided by 5? It's 1. And what's 7 divided by 7? It's 1. And what's 4 divided by 4? Like right here, for example, what's this 4 divided by this 4? It's going to be a 1, or 1 over 1. So that's a big 1, right? Don't think of it as they cancel out. A lot of people say they cancel out. They don't cancel out, they become 1. But when you multiply something by 1, it doesn't really change. So what's this 4 divided by this 4? It's a 1. And what's this 4 divided by this 4? It's a 1. So on the numerator, we're left with a 4 times 1 times 1 times 1 times 4. What's the compact form of that? It is, don't think of 16, think of 4 squared. And that just becomes 1 times 1 times 1. So this just becomes 4 squared. 4 squared over 1. 4 squared over 1 is just 4 squared. I'm just going to write it in that format. And that's perfect. So now we have an equation in 3 different ways. This in the middle, we agree that equals this equation or this expression on the right side. And this one in the middle, also we agree that it equals this one on the left side. Therefore, this on the left side must equal that one. Let's rewrite this down here. So we know that 4 squared, based on this kind of thinking, should be equal to 4 over 5. 4 to the 5th over 4 to the 3rd. And again, I'm probably going to keep that just to make it more consistent. The base of 4 doesn't change, so look at what's happening with the exponents. How can a 5 and a 3 give us a result of 2? Not by addition, definitely not by addition. So let's just look at one more example of expanded. Hopefully last time we need to look at expanded form, just to verify that hopefully what you're thinking does check out. If I had to expand this, it's going to be 8 how many times by itself? It's going to be 8 times 8 times 8 times 8 times 8 times 8. That's 6 so far. Times 8 times 8 times 8. That's 9 of them. 3, 6, 9. That's right. And how many 8 multiplied by themselves on the denominator is going to be 8 times 8 times 8 times 8. And hopefully you recognize this on the left side is the same as this on the right side. All right, let's simplify the ones. You see how many ones do you see? Meaning how many 8 over 8s? I see the first one right there. That's a 1. 8 divided by 8 is 1. 8 divided by 8 is 1. And 8 divided by 8 is 1. That's it. So therefore, this becomes, it becomes 8 to the, what power on the numerator? 1, 2, 3, 4, 5 remain. And because the denominator just becomes 1 times 1 times 1 times 1, this is just 8 to the 5th. Hopefully you're okay with that. That's just 8 to the 5th. Oh, come on. There we go. That's just simply 8 to the 5th. But again, the idea is, do you recognize that another equation we can write in this case is that, let me redo that. This on the left side that we started with can now equal this on the right side that we ended up with. And there it is. And again, I'm going to try and use my color coding here to match. Think of this one as the one in blue. This 9 is the same as this exponent of 9. And this 4 is the same as this exponent of 4. How can this 9 and 4 give us an exponent of 5? And hopefully you already thought the same operation from the previous one. 5 minus 3 is 2 in that order. Be careful, 5 minus 3, all right? So therefore we can rewrite this one as 4 to the 5 minus 3. In that order, and I'm going to keep this in parentheses. Both of those are part of the numerator. And then therefore this is the same as a to the 9 minus 4 in parentheses. That's the main idea, all right? And also keep in mind that the bases are the same. This 8 is the same as this 8. This 4 was the same as that 4, and we have division. Same base and division, we can subtract the exponents. That's the main idea. Same base and division, we can subtract the exponents. Not in whatever order you want. Notice how the exponent of the numerator is 5 minus 3, not 3 minus 5. That would give you a negative 2. And if you did 4 minus 9, that would give us a negative 5. So exponent of the numerator minus the exponent of the denominator. Same base, division in that format. That's the main idea, so that when we get to this, I don't want to write another 9 ends and cancel them out. We can go directly to, all right, we know that this becomes, because it's the same base and division, we can say the exponent of the numerator minus the exponent of the denominator. And that becomes n to the 4th. And that's it. You can eventually start to do them in your head. For right now, I'm just going to write a little bit more steps. This becomes, because it's the same base and division, we can say 7 to the 12 minus 3, which becomes 7 to the 9th power. Same with this one. Same base of 2 and division, we can rewrite this as 2 to the 10 minus 7. That's very powerful for this, what's coming up. And that's the same as 2 to the 3rd. Eventually, some of you will be able to go from here to directly to here, or you probably already can do that, which is perfect. That's the goal. And again, to give you a preview of where we're going, if the 10 and the 2 were in here, we already know how to do this part. So that's where I'm going to begin. 7 minus 3 gives us a y to the 4th. But these are not exponents. These are just coefficients. What's 10 divided by 2? That's just 5. All right, we'll do more complex ones with that later, but same idea, same base and division, we can subtract their exponents in that order. All right, like I said, this is one of the more powerful things to do in this class is to be able to rewrite exponential forms in different formats, whatever, depending on what's given to you. So this is a good way to test what we have seen in the past two type of examples. One of them was adding exponents, the other one was subtracting them. Here we have a mix, and you see them already. What's happening in the exponent here? The exponents are being added. What's happening with the exponents here? Subtraction. What happens with the exponents here? Subtraction. What happens with the exponents here? Addition. And here, addition. And here, subtraction, addition, and subtraction. That way you think either this operation was happening or this operation was happening. What operation do you associate with addition? It's got to be multiplication. So let's start rewriting these. If you need more time, pause it or rewind. But let's check our work now. This better be a 3 to the 7th. You were thinking multiply times 3 to the 2nd. That's it. Doesn't mean simplify it. It just means rewrite it. So this becomes that. It's the same. When we see this, we can think that immediately. And that's going to be a very key idea and powerful, efficient for efficiency. All right. When we see this, subtracting exponents, when do we subtract the exponents? When we have the same base and division. So 5 to the 10 over 5 to the 6. And remember that for these order matters. 5 to the 6 over 5 to the 10 is not the same. But for multiplication, it doesn't matter the order. All right. Again, when do we subtract exponents? When we are dividing the same base. And that's 7 to the 8th over 7 to the x. Notice how it's not negative 6. It's positive 6 here and positive x as the exponent. These are the easier ones. When do we add the exponents? When we have the same base and multiplication. So 4 to the x times 4 to the 3rd. And that's as far as we'll take that one. All right, see if you can do these ahead of me or faster. The same base is 10. We are subtracting the exponents. Therefore, we have 10 to the x divided by 10 to the 4th. And that's it for that one. All right, be careful here. The base is 1/2. We're adding the exponents. When does that occur? When we have 1/2 to the 3rd times 1/2 to the 5th. If we see that, we can think this immediately. These two are kind of cool examples. but there will be future videos about these anyway. Here's the first one. What's the common base? It is 8. And what is happening with the exponents? Subtracting, therefore think division. So 8 to the 0 power. If you don't know what that is fine. That's not the purpose of this video, but that's pretty cool, right? 8 to the 0 power over 8 to the third is really just the same as 8 to the negative third, which is kind of cool. This is the first time we've seen that, but again, that's not the main purpose of this. And then we have some base a. That's not a 9. That's the letter a with the exponent of k plus p. How would we represent that? It doesn't matter what they are, but hopefully you recognize we're adding exponents. Therefore, we're thinking same base, a to the k times a to the p. And that's it for this. Those are the two main, not main, but the two first introductory ideas for exponents. Adding and subtracting them, we're going to use them for the rest of this course. So if you're weak in these, please don't move on. Make sure that this is a very clear idea to you at this point. Otherwise, ask questions or ask for help. All right, so this was kind of fun for me, even though it's very basic idea. I rarely have fun time doing basic videos, but these really are conceptual and a nice time to have to spend doing some math. All right, so I hope you don't want to listen to me talk anymore, because I can talk for another 4 or 5 minutes, even if it's not about math. Or I can talk like another 15 minutes about math, but I'm not going to do that. That's the end of the video. Go enjoy the rest of your day, all right? Goodbye.